So, you want to go to space? What's a rocket anyway? Hello, science fans. Have you ever looked up at the moon or the stars and thought, wow, I'd love to go there? Well, getting there is a big, big job. You can't just take a car or a plane. The sky goes up, 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 and eventually, the air runs out. That's where space begins. A place with no air to breathe and nothing for a plane's wings to push against. We need a rocket. What's a rocket anyway? Hello, science fans. Have you ever looked up at the moon or the stars and thought, wow, I'd love to go there? Well, getting there is a big, big job. You can't just take a car or a plane. The sky goes up, up, and eventually the air runs out. To make that incredible journey, we need a special kind of vehicle, a machine designed to travel where there's nothing to push on but itself. We need a rocket. It's not just a vehicle, it's a cosmic powerhouse built for the ultimate road trip. Think of it as a super strong, super sleek tube packed with power. Its main job is to push itself away from the Earth with so much force that it can escape our planet's pull and fly into the vast emptiness of space. Unlike a jet engine, which needs to suck in air from the atmosphere to burn its fuel, a rocket carries everything it needs with it. It brings its own fuel and its own oxidizer, the stuff that lets the fuel burn. This self-contained design is the key. Now, how does a rocket actually move? It's not magic, it's science. And the science is all about a brilliant idea from a very smart person named Sir Isaac Newton. He came up with 3 laws of motion, and the third one is the secret sauce for all rockets. Newton's third law says, for every action there is an equal and opposite reaction. It sounds a little fancy, but the idea is super simple. If you push on something, that something pushes back on you with the exact same amount of force. Imagine you're standing on a skateboard and you push against a wall. What happens? The wall doesn't move, it's very big and heavy, but you and your skateboard roll backward. You pushed on the wall, that's the action, and the wall pushed back on you, that's the reaction, sending you on your way. The rocket does the exact same thing, but instead of pushing against a solid wall, it pushes against its own fuel. It's a very clever way to move without needing anything external to push on, which is perfect for the emptiness of space. You don't need to build a rocket in your backyard to see Newton's third law in action. It's happening all around you, all the time. You are an expert in action-reaction physics, and you may not even know it. Think about blowing up a balloon. You fill it with air, pinch the end, and then you let it go. The balloon zips and zooms all over the room. Why? The air rushes out of the opening. That's the action. And this pushes the balloon in the opposite direction. That's the reaction. The balloon is like a mini rocket, powered by escaping air instead of burning fuel. Have you ever jumped off a small boat or a canoe onto a dock? When you jump forward toward the dock, action, the boat gets pushed backward, away from the dock, reaction. Your body pushes off the boat to move forward, and in turn, the boat gets pushed back by your feet. Even something as simple as walking is governed by this law. When you take a step, you are using your foot to push the ground backward. The earth pushes back with an equal and opposite force, propelling you forward. So, we have our rocket, and we know that pushing gas down will make it go up. Simple, right? Well, there's a big invisible force trying to stop it. Gravity. Gravity is the force that pulls everything toward everything else. Because the Earth is so incredibly massive, it weighs about 13 septillion pounds. Its gravitational pull is very, very strong. It's the force that keeps you and me and everything else stuck to the ground. It's what makes an apple fall from a tree and what keeps the moon in orbit around our planet. Gravity is always pulling down. For a rocket sitting on the launch pad, gravity is like a giant invisible hand holding it down. The rocket might weigh millions of pounds, and gravity is pulling on every single one of those pounds. Before it can even begin to climb, the rocket has to overcome this immense downward pull. It's not enough for the rocket's engines to just create a little push. The upward push, which scientists call thrust, has to be greater than the downward pull of gravity. To escape Earth's gravity completely, a rocket must reach escape velocity, about 25,000 miles per hour or 11 kilometers per second. So how does a rocket win this monumental fight against gravity? It all comes down to creating a truly massive amount of thrust. The rocket's engines are designed to be fountains of fire, turning massive quantities of fuel into an even more massive blast of hot gas. The sheer force of this downward blast is what gives the rocket the edge it needs. To achieve liftoff, the thrust generated by the engines must be greater than the total weight of the rocket. This isn't just a small victory. The thrust needs to be significantly larger to lift the rocket and accelerate it upwards at an incredible rate. Think of it like an arm wrestling match. Gravity is your opponent, with a constant, strong downward pressure. Your rocket's engine is your arm pushing upward. To win, you can't just match your opponent's strength. You have to overpower it. Rocket scientists and engineers calculate the exact amount of thrust needed. They design engines that can burn tons of fuel every single second. For example, the powerful Saturn V rocket that took astronauts to the moon generated over 7.5 million pounds of thrust at liftoff, all to lift its 6.5 million pound weight off the ground and send it soaring into the sky. As the rocket climbs, it's constantly burning fuel, which means it's getting lighter. Imagine climbing a mountain while carrying a heavy backpack. As you lighten the pack, climbing becomes easier. With less mass to carry, the same amount of thrust can push the rocket upward even faster, helping it reach the high speeds needed for orbit. The moment of launch is one of the most exciting and intense moments in all of science and engineering. It all starts with ignition. Deep inside the rocket's engines, a spark, a chemical reaction, ignites the fuel oxidizer. This creates a controlled, sustained explosion that just roars to life. For a few seconds, the rocket is held down on the launch pad by powerful clamps as the engines build up to full thrust. This is to make sure everything is working perfectly before releasing this beast. You can see clouds of steam and smoke billowing out as the engines prove they are ready for the big push. Then comes the command: liftoff. The clamps release, and for the first time, the rocket's upward thrust is greater than its weight. Slowly, majestically, the colossal machine begins to rise. It seems to move in slow motion at first because it is so incredibly heavy. But as it climbs, it picks up speed, faster and faster. The sound is deafening, a crackling roar that can be heard for miles around. It starts by going straight up, but soon it begins to tilt, following a precise, curved path called a gravity turn that helps it achieve orbit. Finally, the sky changes from blue to black. The first, most violent part of the journey is over. A rocket might look like a simple tube from the outside, but inside, it's a marvel of engineering with several key parts working in perfect harmony. Let's look at the main components. First, you have the structural system, which is basically the rocket's skeleton and skin. This structure has to be both incredibly strong and as lightweight as possible. Next are tanks, huge containers for fuel and oxidizer. At the top is the nose cone or payload fairing that protects the payload. Then the heart, the propulsion system, rocket engines, fuel tanks, oxidizer tanks, pumps, and plumbing. Pumps like turbopumps pressurize fuel and oxidizer to feed the engine. The fuel might be liquid hydrogen or refined kerosene. The oxidizer is usually liquid oxygen. Then there's the brain, the guidance system and flight computer. Sensors like gyroscopes and accelerometers tell the rocket how it's moving. Tiny adjustments via gimbaled engines and small thrusters keep it on course. The reaction control system handles attitude control in space. At the top is the payload. Satellites, telescopes, cargo, or crew. All systems must work together flawlessly for a mission to succeed. Have you ever wondered why rockets look like different sections stacked on top of each other? Well, they are. These sections are called stages. Using stages is one of the cleverest tricks in rocket science. A huge portion of a rocket's initial weight is just fuel. Once a tank is empty, the rocket still carries that big, heavy, empty tank. Extra weight just slows you down. So rockets are built in stages. A typical rocket might have 2 stages or 3. The first stage is the biggest and most powerful. Its job is to lift the rocket off the ground and through the thickest part of the atmosphere. After a few minutes, its fuel is used up. Then the rocket jettisons the entire first stage. Explosive bolts fire, and the massive empty booster falls away. The massive empty booster often falls into the ocean. Now the rocket is much, much lighter, and the second stage can ignite. Its engine can be smaller and more efficient, pushing the lighter rocket even faster. If there's a third stage, the process repeats until the payload reaches orbit or heads to another planet. Modern rockets design first stages to be reusable. They fly back and land, ready to be used again. That reuse lowers costs and is the next great evolution in staging. Shedding weight as you go makes the rocket far more efficient. It's a brilliant solution to gravity and mass. Consider the following. So, why should we care about all this rocket science? It might seem like something only for astronauts and super geniuses in lab coats, but the truth is, understanding the basics of how rockets work is useful for everyone. For starters, it's a fantastic way to see science in action. Newton's laws and the fight against gravity are the same principles that govern everyday life. How a ball flies through the air is related to these same ideas. Space tech has produced everyday inventions, called spin-offs. Memory foam for beds, scratch-resistant lenses for glasses, cordless power tools, tiny cameras in our phones. Space challenges force us to make things smaller, lighter, stronger, and smarter. The quest to explore pushes the boundaries of what's possible. Understanding rocket science inspires us. It shows what we can accomplish when we work together on huge problems. Be curious. Ask big questions. Pursue your own goals. The journey to the stars reminds us of human curiosity and our desire to explore the unknown. Finally, space will become even more important to our lives. Next time you see a rocket soaring into the sky, know it's not just a machine. It's a symbol of science, innovation, and the incredible things we can do when we reach for the stars.